Okay, hello Year 10. We're moving on to a new topic now. We're moving on to forces. So if you look at the work folder, we've done all of this so far. This is today's lesson, forces. And I'm just going to go into the PowerPoint, which is just here. Now, we should remember forces from before. We've done it in Key Stage 3, and we do talk about it quite often when we look at different physics topics. But the important thing is contact forces versus non-contact forces. Now, your contact force, okay, will be something that you need to touch. Okay, so this is it. Right? Contact force is something that you have to touch. For example, friction. If you rub your hands together, you have to touch your hands to make friction. Air resistance. When you put your hand out of a window of a car, the air particles have to touch your hand. They bounce off your hand, and that's why you feel it as air resistance. Non-contact forces act at a distance. Now, gravitational, electrostatic, and magnetic forces are the only three you need to know. If you remember that these three here are your non-contact force, every other force that you are asked about will be contact. So, free body diagrams. I'm just going to draw what they've put on this slide because I think it's easier if it's drawn and explained at the same time. So let's see, you've got this dude here, stood on the moon. Now, there are two forces acting on this person. So this person, I'm going to draw them as a circle. You can draw them as a circle or as a square, like in this diagram here. So there they are. We call it a free body diagram because we simplify everything. We only look at everything we need to know. Now this person has a weight. I can put that as a W. The person has a weight acting downwards, but they are stood on the floor. So that floor pushes them up. The floor pushes them up. No. Okay, and that is called the normal force or the reaction force. So I'm going to put N. Now, when you look at a free body diagram, in this case, because this person is stood still, they are not moving, this force here and this force here will be equal and opposite in direction. Now that is a free body diagram. Same over here. If you were to look at, let's say, this person. There's the person, they are this square here. The water is pushing them upwards, that is the upthrust. Their weight is pulling them down, that is their weight force. The diver is pushing them. This is simulating weightlessness in space and what happens if you lose control, you've got to regain control. And the water is dragging them back. So these four arrows show the forces, but if you look, this force is much bigger, so this person will be accelerating that way. Now, so a force is a push or a pull. It acts on an object because something else has interacted with it. Forces are vector quantities, which means they have a magnitude and a direction. So a magnitude, this is really important. Vectors are really important. You do them in maths as well. Magnitude just means size. So if something has a size and a direction, it is a vector. We know that forces are measured in newtons with this unit. Let's look at a scalar versus a vector. If I asked you to measure something, let's say the length of your phone, and it comes out at 33 centimeters. This is just a number, so that is a scalar. Right, that is a distance here. Displacement. If you went on Google Maps and Googled the corner shop or the nearest shop to you and asked for directions from it, the map would give you a path to follow. And it would say this will take you 5 minutes and you're going 75 meters or something. Maybe longer than that. It'd be about maybe 600 meters. It would say you need to go 500 meters down this road, you need to go north 100 meters, and then you need to go east 50 meters. Now it simplifies it for you because it just points you in the right direction, but that's what it's doing. Google Maps is showing you a vector to get to your store or wherever you need to go, because it has a distance and it has a direction. So here's your distance and there's your direction. So a vector is a distance plus a direction. Okay, you represent vectors drawing an arrow. The length of the arrow shows the magnitude. Remember, that's the size. The direction of the arrow shows which way you have to go. Let's have a little look. If I was to draw a force of 5 newtons acting downwards, first of all, make sure that my arrow is pointing down, and if I had, this would probably be 5 centimeters long, this arrow. A woman walks 4 kilometers north, same idea. I'd probably make this 4 centimeters tall, and I'd say that 1 centimeter equals 1 kilometer. I'm sure you've seen that on the side of maps before. Now, let's talk through these. So a woman walks 4 kilometers north. She walks 4 centimeters north. She walks 3 kilometers south. If she walks 3 kilometers south, she goes back the way she came, but she ends up here. Okay, so let me draw your... It's hard because it's not different colors. She then runs 4 kilometers east. Oops. She then runs 4 kilometers east, like that. What is the displacement from her original point? You'd have to use Pythagoras for that, which we're not going to do, but you can see these 3 vectors. The first one told her to go up, the second one told her to go down but not quite as far, and the third one told her to go to the right or east. This is how you use vectors to navigate, and this is why it's important they have a direction, because it tells you a bit more. Okay. Scalar of vectors. I've got the answers here, but we should know that temperature is just a scalar. It's just a number. It's 21 degrees outside. There's no direction. Same for energy. Velocity, that is speed, but with a direction. Mass, speed, distance, the scalars. Displacement is the vector. Now, velocity and speed are related because velocity is the vector, speed is the scalar. Makes it easy to remember, right? Because velocity is with a V and speed is with an S. We also have distance and displacement. You know distance. You always talk about distance from somewhere all the time. So that one is your scalar and displacement is your vector. Now, I'm going to exit this. Discard my ink. I'd like you to quickly, now that you've listened to me talk for 5 minutes, I'd like you to look at this. I want you to try and do these 3 body diagrams, and if you look, the answers are there on the next page. So let's just say I was doing this duck here. Duck has a weight, right? There's the duck's weight. The duck is floating and is not moving. So for this duck to be not moving, all of the forces on this duck need to be balanced, and for that I would need my reaction force or my upthrust from the water. I'm going to call it upthrust. Notice how this is equal in size. At least I've tried to make it equal in size, but it is opposite in direction. So if I added this arrow and this arrow together, they would cancel each other out, making 0. So this duck would just be floating. So have a look and try and have a go at these 3 body diagrams. And then check your answers on the next slide.